All right, so let's look at capacitor. Remember I told you guys capacitor was two parallel plates? Boom, you just saw it. You guys saw like the inside cylinder, the outside cylinder. And you guys saw it spark right there? Okay. Now, this capacitor actually has a special name. It's called a Leyden jar. So this is what scientists were excited about all in the 1700s. Ben Franklin worked with these a lot, these Leyden jars, because they could store energy temporarily in these electric fields. Okay. So then they pull this apart. I've got this guy muted just to see if things go on a bit here. But one thing he said, one point that he makes is that when he touches these together, there's actually no spark. Okay? But he touches this plastic separator, which back in the day would have been made out of glass, right? It feels all prickly. So actually the charge build up on that. So it's kind of interesting point there. He puts it back together and then he charges this thing up and then like store energy temporarily. Right? Electric field. Let's look at another one with capacitors. Ooh, now this it's called an ultra capacitor. It just means it's a very large capacitor. Remember I told you guys capacitors are measured in farads. Ooh, this is 2,600 farads. So like we're talking about thousands of farads, right? There's 2,600 farads. Right? Well, what is a conventional capacitor? Like if you take apart just some electric appliance or you find some old TV set, what is this here? It's 516 microfarads. Micro, that's like a millionth of something, right? And this would be a pretty big capacitor to have just on a conventional circuit. So like normally you're working with microfarads, but somewhere you found something that has like thousands of farads, which is like a billion times the capacitance. Right? How much energy can you store in a capacitor? That was on that poster I just showed you guys too. So 1/2 CV squared. C is the capacitance, V is the voltage. Right? Oh, that looks kind of analogous to 1/2 MV squared, doesn't it? Or some version of that. 1/2 KX squared. How about that? Okay. Right. So again, this is kind of like a battery in the sense that it's storing energy, but it's not a chemical battery. It's just energy stored in electric fields. So capacitor, right? Starts frying stuff with this, right? Talks a little bit about this, but skip that ahead a little bit, right? And then, okay, yeah, then he connects a bunch of capacitors. Now, remember, if he connects them in parallel, that's the way to increase capacitance, right? Right. Versus, so it has offset rules that resistors and inductors do. Right? Store energy there. All right, let's switch over and look at inductors. Inductors. Right. Oh, look at that. It's literally a coil of wires. That's it. You put an inductor, put a wire into a coil, boom, you have an inductor. Now, if you run a current through it, that will create a magnetic field. That's what these blue lines are. Those are magnetic field lines. Right? Now, that would be a temporary magnet because as soon as the current stops flowing, then, well, it takes a while for the current to dissipate because it's an inductor. That's what an inductor does, right? But the magnet field will go away. So that could be an electromagnet. That's what that is. Oh, look at that. You flip the on switch. It takes a while for the current to build up. That's what an inductor does. It causes the current to lag. Flip the switch off, and the current still flows. It just dissipates, and it takes a while for the current to completely turn off. Ah, so put that guy in there. Let's say some inductive coupling. I know he has at some point. Here we go. Here we go. Right. So he's got an inductor here, and right beneath it, a separate inductor. Right. And then here we go. Right. Remember I told you guys about inductive coupling. So if one of these he has a current running through and the other one is just hooked up to, say, a voltmeter, right? Well, the one that has current running through it is going to create a magnetic field. That's what an inductor will do, create an electromagnet. And then the other one's going to pick up that magnetic field and it will induce a current on that side. So you have wireless transfer of electricity. Right? That's what he's picking up there. Right? Wireless transfer. It's called inductive coupling. Okay? And if those had different numbers of coils, then the voltage and the current would be different. Right? Let's look at a different example of inductive coupling. Okay? So got a voltage source in the back. It's going to flip this on. You see a little green light come up here. Boom. That's it. Turn on. Okay? And now there's a current flowing through this giant ring. Hey, that's like an inductor. Going to pop in a light bulb here, and boom, light turns on. Okay? What's the energy source for this light? It's actually this black box over here was connected to the grid. Okay? Oh, he gets it closer. Look, it gets a little bit brighter. Right? Okay? Again, because the current flowing through this large ring creates a magnetic field. The small ring on the right picks up that magnetic field and then creates a current that way. Did you guys see it flicker off? It flickered off. Right. So remember, if these aren't aligned the correct way, then the magnetic field and the current won't transfer. Right. Turns at 90 degrees. Oh, turns off. Right. Right. Think about that right-hand rule. Need the vectors to align. Right. All right. Let's look at another example of induction. Try to unmute this one. Inductive heater. induction heater. Ooh, so that's pretty fun. Okay, here's maybe a better looking version of Lenz's law that I was showing you guys. Remember, I had that copper casing in that magnet. Notice that the magnet is not attracted to that copper, right? Because copper is not ferromagnetic, right? So you can't pick it up with the magnet. Oh, but look at that, right? It drops the magnet through and it takes forever for it to fall. So it's the same demo as I had up here, just it looks a little bit better, right? Right? So again, why is that? Because as the magnet falls through that copper casing, which is a closed loop, right? See, if this was like a C shape, then it wouldn't be a closed loop. So this wouldn't work. But in fact, it's a complete O, right? Creates a magnetic field, which creates eddy currents and creates its own magnetic field, which resists the original magnetic field. So, positive, right? So there's some energy being transferred as it falls through, right? There's some work, some kind of resistive force times resistance. And if you had that hooked up to a power grid, then you could transfer energy, that force times resistance, across the power grid that way. Okay. Let's look at simple motor. I want to have you guys do something kind of like this later this week. Not exactly this model, but not too far off. So pause this right at the time here. He's got some magnets here. He's got a battery, like a voltage source. Oh, and look at this wire, which can complete a circuit. So there's about to be a current flowing through. Now, if there's a current and there's a magnetic field down here, current magnetic field, hey, what's that going to create? How about a force, right? Right hand rule, it's going to create a force. Right? Let's check this out. Oh, look at that. Right? That's a motor. That's a basic motor right there. Right hand rule. What if here? What if we rewind this? What if you flipped the magnets upside down? How would that change things?
Well, it's spin the other way.
Exactly, it would spin the other way, right? Because the direction that it's rotating has to do with, yeah, what's the direction of the current flow in the magnetic field down there? Oh yeah, yeah, yeah. Right. Hey, how about the same thing if you left the magnets the same, but you flipped the battery upside down? That would reverse the direction of the current, which again would change the direction that that thing rotates, right? So have you guys do something kind of like that later this week? Let's see what else I got here. Here, let me open up some different demos. Let's look at some magnetic fields here. All right, so what's a magnetic field? Okay. I think the main theory of what causes magnetism has to do with like spinning electrons. If you can get electrons to like spin one way and that. Right. Oh, okay. So he has these magnets. Shows their magnets. Goes on some paper clips which have some iron in them. Right. Throws a paper over top. Throws some iron filings. Yeah. Okay. So that's kind of what I was showing you. Sort of. Yeah. I think it's a little bit better example. One thing you can do that's pretty cool is you can take a magnet and put it in a flask and throw in those iron filings, and you can see a 3D magnetic field. Of course, that breaks eventually, but there, right? So you guys saw those magnetic field lines. Now, conventionally, people draw the lines going from north to south. Again, that's just like a man-made convention, but that just tell you something about direction. Then you can figure out how to construct a motor or a generator to figure out direction to make things move. Right? So we got field lines drawn north to south. Right? There's a single bar magnet. You guys see that the field lines don't cross, right? The field lines don't cross going from north to south here. What if you put two magnets close to each other? Okay, well, if they're north to north, they're going to repel. Right? Again, the field lines don't cross. But if you line them north to south, then you get just one giant bar magnet there. Yeah, magnet field. Right, let's take that another step and look at, okay, so there's a magnetic field. Again, if it's a giant magnet, then maybe the field lines are approximately parallel like they are there. And what if you rope off some area? That's what that red square is, right? Area. Then flux could be the field times the area. That's what the Greek letter phi could be flux. So field times area, where if you increase the area, you're going to increase the flux. That makes sense, right? There's also a cosine component thrown in here. So if you say rotate that area so that say everything's aligned like that, then you don't get any flux because there's no area for the field to go through. You guys see that too? So okay, and then turn it that way. Now, what if you had a coil of wires going around the outside of that square? As you're rotating it, you're changing the flux. And now we're back to Faraday's law, where as you change the flux, then that will induce a voltage, right, which can go on to create a current, and boom, you have electricity, right? Right, what if you have like a weird shaped area? Then the only area that matters is what's, say, like perpendicular to those field lines. So like that. Let's look at, right, how about Earth's magnetic field? Like, why does Earth have a magnetic field? Let's say with that. One thing I want to have you guys do later this week too is probably build a basic compass, which you can do if you either hang a magnet from a string, a bar magnet from a string, the poles will align with Earth's magnetic field. Or I think what I want to have you guys do is put bar magnets in a cup and then put that cup in water so it floats around. And then that will naturally align. If as long as you have the poles aligned horizontally, right, then it'll rotate and the magnet will line up with the magnetic field lines of the Earth. Well, why does Earth have a magnetic field? The main theory is the fact that Earth's mantle is molten and it has a lot of ferromagnetic materials in it, like iron, for example. Like iron, nickel, and cobalt, I think, are the three main ones. So when Earth was forming about 4.5 billion some years ago, a lot of the heavier elements tended to sink down into the Earth. Right? For example, gold. Right? Gold is really dense and heavy, so there's not very much of it on the surface. Right? There's a lot of gold inside the Earth, but we can't really access it. Right? So iron, for example. You guys remember how hurricanes form back last semester? You guys remember Coriolis effect? Right? So when winds change latitude, the Earth rotates at the same angular velocity everywhere, but different linear velocities depending on your latitude. Right? There's a similar type effect going on inside the Earth, right? And then you get these rotating streams, right, of these ferromagnetic materials. Right? So ferromagnetic materials on the move. It's creating a giant magnetic field. That's good. We have magnetic field because that protects us from a lot of cosmic radiation, solar rays from the sun. Right? So yeah, you can see that here. It's like here's the geographic north, here's geographic south, right? And then here's these cosmic rays seeping in there. Right? And we can see that from the surface. So here you guys are going to see the northern lights. So this is up in Norway. Down in, like, I'll show you in Antarctica, sometimes you can see a similar thing with southern lights. I think it's like a time lapse going on here, so like sped up. Right. Yeah, so there you go. There's those cosmic rays. Oh, so I guess I should mention Earth's north and south magnetic poles are shifting around a bit, so that they aren't completely stable. They probably flip every like so often, and scientists know that because if you look at either like igneous rocks that came out of volcanoes and then cooled, or if you look at ice samples like ice cores, right, you can see magnetic field lines shifting around because if there's anything that's ferromagnetic, it will align with like little dust particles. It will align with Earth's magnetic field, and those change periodically. Right? Another thing too is the North Pole and the South Pole are actually oppositely named. So oops. Because how was the north side of the magnet named? Well, it was just the side that pointed towards the north. But you guys know that north and south actually attract. So up in Canada is actually the south magnetic pole, and down in Antarctica is actually the north magnetic pole. It's actually opposite. So it's like backwards. Oh, here we go. Here's got a slide on Earth's moving magnetic pole. So here's where these are islands in northern Canada. So way up in northern Canada, right? And over time, the well, I would say the North Pole has been shifting, but you guys know it's actually a giant South Pole, right? Okay. We're talking about the magnetic pole. Right? Ooh, hey, it's pretty fun. Magnetoreception. So some animals have this as a sense that that humans don't really have. Right? They can actually navigate magnetic field lines using magnetoreception, magnetoception. Let's look at diamagnetism. So if you think magnetism, you probably think of ferromagnetism, which is only a type of magnetism. So say like when you pick up paper clips with a magnet, that's because the iron in the paper clips is attracted to the magnetic field. Now, some materials are actually always repelled from magnetic fields, including water. Water is weakly diamagnetic. The strawberry is mostly water, right? So you put this in the magnetic field and it's going to repel from the field, right? Float around like that. Yeah, if you take a magnet and put it next to the surface of, say, a bowl of water, it will actually depress the water a little bit, compress it a little bit. Right? Now here's this would be a really strong magnet to make that happen, right? So Scott one with the frog. Fun days. Oh yeah. Floating around in the magnet. Let's watch some Paul Hewitt. Paul Hewitt.
The source of that magnetism was betrayed years ago, more than 150 years ago, by a fellow by the name of Hans Christian Ørsted, who was a professor type teaching, I believe he was in a high school classroom. And he was showing the students that there's no relationship between magnetism and electricity. The physics books at that time had electricity as one subject and magnetism as another. And Ørsted was showing there's no relationship between the two. And one of the things he would do is he would line up the piece of wire like this and put it over a magnet and pass a current through it. And you really don't see anything happening. There's no interaction. But after class, a student came up and held the wire in this direction. And when a current passed through it, okay, watch this. When a current is passed over the wire like this, boom, you see that interaction? It turns out there's an interaction between a current carrying wire and a magnet. And it turns out, to make a long story short, the source of all magnetism is moving electric charges. And when the charges move through the wire, they set up about the wire a magnetic field. And that magnetic field is in concentric loops around the wire. If I pass this wire through a hole in a piece of paper, and I put a whole lot of little compasses around the wire, and no current goes through, all those compasses would point north. But you know what would happen if I put a current through that wire? Bam! All the compasses will line up with the field. And it turns out that field, it takes the shape of concentric circles about the wire. The further away you get, the weaker they get, but the direction is all that way. So surrounding every current carrying wire is a magnetic field that takes the direction of the concentric circles. I want to show you something that's even more interesting than what we've seen. Let's take this magnet. I'm going to put the wire in the magnetic field of this magnet, and I'm going to touch this momentarily so I get a pulse of current. And when I do that, when a current goes through this, would this wire, in a sense, be a magnet? How about when no current goes through it? It's copper wire. Copper is not ferromagnetic. Copper, you've all tried when you were a kid to pick up a penny with a magnet. It doesn't work, does it? Because the penny's copper, okay? So the only way you're going to get magnetism with copper is to have electrons flowing through it. Electrons flowing through anything would set up a magnetic field around that anything, yeah? Let's see what happens with the magnetic field of the wire and the magnetic field of the magnet. Let's see if there's any interaction. What do you suppose? Watch this, gang. You see that jump down? See that jump down? Let me turn the magnet around. Jumps up. Did you see that? I'm going to do it one more time. Watch. Wow, jumped up. So one way it jumps up, and the other way, put it this way, it jumps down. I wonder if that jumping motion could be harnessed. How many people say, well, no, there's probably no practical application of that. Wires will move in magnets. Big deal, right? Is it a big deal? It's a very, very big deal. Because guess what this underlies, gang? Electric what? Begin with M, end with odors. Try it. Motors. Any electric motors be working on such principle, okay? And dig this. Whenever you see any electric motor, realize, you know, sometimes we see things and we're so overwhelmed with the complexities, we don't know what the nitty-gritty is. Realize the nitty-gritty of an electric motor is simply a current carrying wire being deflected in a magnetic field. Period. That's it. This was done by a couple of physicists about the same time in history. One was Michael Faraday, a Scottish guy in England, and the other was Joseph Henry, an American type in Vermont in the 13 colonies. And they both at the same time found the same effect. And here's what they discovered. They had meters similar to this at that time, but they didn't know how to get electricity. Well, they got electricity from batteries. fellow by the name of Volta, Alexander Volta, Italian type, made batteries, and that was kind of nice. Everyone's excited about electricity. And then Michael Faraday and Joseph Henry discovered the following. No batteries over there again. No batteries, no tricks. Magnet, wire, meter. Watch this. You see anything?
No.
Faraday didn't see anything either. Okay. And but watch this. Henry didn't see anything either, but watch this. Did you see something? Again. My goodness. My goodness. There's no battery nearby, and guess what we are generating? Begin with EC. Electric current. I am generating electric current. And Faraday and Henry found out that. No batteries, no cells, no lightning, none of that. Just the motion of a wire in a magnetic field. So Faraday goes to bed and he's really excited about that. And while he's in bed that night, I'm making this up now. While he's in bed that night, he's kind of thinking, gee, I wonder what would happen if I did it with 2 wires. So he gets up in the middle of the night, takes his candle, goes downstairs, had to do a candle. Little did he know that he was going to get rid of candles, honey. The candle industry was furious later on, okay? But what he did is he went down and he took 2 wires. And guess what happens with 2 wires, gang? Poof! Twice as much current. Goes back to bed. Then he thinks, I wonder, 3 wires. Shall we try it? Didn't sleep the rest of the night, gang. I wonder, 1,000,000 wires. What do you think? 1,000,000 times as much. Okay? This is a remarkable discovery that one can, it turns out, induce voltage by simply moving a wire in and out of a magnetic field. And so Faraday's discovery is couched a little differently. Today it's called Faraday's law. And what it says is this, a little more complex. Change the magnetic field in a closed conducting loop of wire, doesn't even have to be conducting. Just change the magnetic field intensity in a closed loop, and you will induce a voltage in that loop. Now this loop happens to be a copper wire, so the voltage in that produces a current. So look at this, you get a current. Change the magnetic field in 2 loops of that closed copper wire, 2 loops of that circuit, and guess what you get, gang? Twice as much voltage. 3 loops, 3 da 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 da. So that's the rule. All you got to do is change the magnetic field intensity, and you will induce a voltage, which will produce a current if you're talking about a conductor. Ain't that neat? That is really, really nice.
All right. Then they had electricity generation. All right. Last couple things for you guys to take off here. Just you just mentioned another video, interesting application of electromagnetic induction, which you've probably seen if you just drive around the streets and pay close attention. You guys ever seen a pattern on the road looks like this? Right? Kind of hard to, yeah. If you haven't, then look real close because you'll see this as you're driving around town. This is a wire buried underneath the road, which is connected to the traffic signal. So when your big car going across, it has a bunch of iron in it, right? Drives across the thing, that will change the voltage a little bit, which will create a current and it will trip the wire. So the traffic light knows that your car is there. Now that's related to the fact that Earth is in a magnetic field. Okay, I'll stop there. All right. See you guys Wednesday.